Hi everyone, it's Dr. Nigro back with another screencast dealing with our second unit, vertical motion. This time we're going to be talking about free fall. All right, so first we should define what free fall is. All right, so as we saw in our videos, it's any motion that occurs under the influence only of gravity. So occurs when an object is moving due only to gravity. All right. So the direction that an object moves when it's in free fall is got to be vertical. So you're either moving up or you're moving down. Now for our directions, we're going to decide that positive is up and that negative is down. All right, so when an object is in free fall, what is causing its acceleration? Well, that's going to be gravity. All right. Now, gravity is going to vary depending on where you are in the universe, but since we're here on Earth, we tend to use 10 meters per second squared, right? But again, this is on Earth. So if you're somewhere else in the universe, you'll need to know the gravity value there. All right. There are three types of free fall problems we're going to run into. The first is called dropped. All right. So that's when you're holding an object and you drop it and it moves towards the Earth. The second is tossed. That's when you toss an object up into the air. And the third is both combined. So we call those up and down problems. All right, we're going to look at each of these. We're going to talk about the position and velocity graphs that go along with them, and then work a problem. All right, so first we're going to deal with dropped. All right, so you can see I have my figure. So I have an object, a ball that is dropped down towards the earth and will eventually hit the ground at the bottom. All right, so there are a couple pieces of information that are known just because it's a dropped problem. The first is that the initial velocity of the ball is going to be 0. All right, as the object falls, it will gain velocity until it reaches a certain value. That'll depend on how far it's falling. The entire time that it's falling, the acceleration is negative 10 meters per second squared because of gravity. All right. If we look at the graph that goes along with this, we have a distance versus time graph. All right. The ball starts away from us and moves towards the earth. All right. And if you think about that motion, hopefully you recognize that that object speeds up as it heads toward the earth. So we're going to get a curve because we have acceleration, and it's going to start flat and then steepen as that velocity value starts to increase more and more. All right, for our velocity versus time graph, all right, the motion is negative because we're going down. So all of our, our velocity graph will be below our 0 axis. It's going to start at the axis and move away from 0 because it is speeding up, all right? And with our earlier experiments, the slope of this line equals the acceleration of the object, and hopefully it will be around 10 meters per second squared. All right, so anytime that you deal with a problem where you're dropping an object, the ball has maximum velocity at the bottom of the motion. Now, this is not after it's hit the ground. This is right before it hits the ground. All right, and then the velocity of the ball equals 0 at the maximum height at which the object is held. All right, so that's dropped. So let's look at a problem. All right, Zumanjaro is a free fall ride at Six Flags Great Adventure in New Jersey. The ride is 415 feet tall, which is 127.7 meters, and reaches a top speed of 112 miles per hour or 50.2 meters per second. What is the ride's acceleration as it falls from the top, and how long should the riders take to reach the bottom of the ride? All right, so let's think about what we know here. The object is falling, all right? The initial velocity is going to be 0, all right? And then its final velocity will be 5.2 meters per second, all right? We also know that it's going to fall a total distance of 127.7 meters. All right. Now, in addition to this information, because it's in free fall, we know the acceleration. It's due to gravity. So we put negative 10 meters per second squared in. And then our unknown for this problem is going to be time. So looking at the information I have, my easiest formula is going to be the acceleration formula. All right, where I solve for time. So that's going to be equal to v final minus v initial over acceleration. And in this case, 50.2 meters per second minus 0 over negative 10 meters per second squared. Now, I should say that because the object's falling, the velocity also should be 0. All right. When you're working these problems, time should never become negative. Time is one that always has to be positive. So don't be surprised. All right. That may mean that you need to check your signs. All right. So we do our division and we find that it's going to take our object 5.02 seconds to fall from its maximum height to the bottom of the ride. All right. All right. So our second type of free fall problem is a tossed up problem where an object is tossed up into the air. All right, so similar to what we saw for drop, there's some pieces of information that we know. All right, this time we know the velocity of the object at maximum height is going to be 0. All right, the initial velocity is going to be an unknown, and it depends on how much force your arm puts behind the throw. All right. As the object moves up into the air, it accelerates due to gravity, which is negative 10 meters per second squared. And so because our velocity values are going to be positive and our acceleration value is negative, we should see our object slow down as it moves up into the air. All right. So if we come to our distance versus time plot, all right, the object starts close to us and moves away. And because it's slowing down, it's going to steep and then flatten out. All right, for our velocity versus time graph, all right, this time our velocity values are all positive. So we're going to start on the positive side, but it needs to go towards 0 as the velocity decreases as it reaches its maximum height. All right, so the ball this time will have maximum velocity at the bottom, the initial throw, all right, and the velocity of the ball again equals 0 at maximum height. And we're going to see a theme in that maximum height is where everything is 0, and the initial bottom is where we see the maximum velocity values. All right, so let's look at one of these problems. All right, Kate is riding the slingshot at Six Flags Great America. Once loaded into the ride, the slingshot shoots Kate into the air with an initial velocity of 25 meters per second. How long does it take her to reach maximum height? And then how far up into the air does she travel? All right, now this problem only gives us one number. It tells us the initial velocity is 25 meters per second, but we do know some other information. We know that at maximum height, she's going to have a velocity of 0 because she's being tossed up into the air. We also know this is free fall because nothing is moving her once the ride releases her, so she'll be moving with an acceleration of negative 10 meters per second squared. All right, so our first job is to figure out, well, what is the time it takes to reach that maximum height? All right, and again, I'm going to use my acceleration formula rearranged to solve for time. So I get time is equal to v final minus v initial over that acceleration. And I find that time is equal to 0 minus 25 meters per second over negative 10 meters per second squared. So the time that it's going to take Kate to reach the maximum height is 2.5 seconds. All right, the second part of the problem wants to know, well, what is that maximum height? All right, so here you have a couple choices. You can use your distance formula and solve for distance, or you can use V average. All right, I'm going to just use the distance formula. It's a little unwieldy, but it has everything in it. All right, so we've got our V initial times time plus 1/2 AT squared. All right, so for our initial velocity, we have 25 meters per second times our 2.5 seconds plus 1/2 times negative 10 meters per second squared times, oh, I didn't give myself a lot of room, 2.5 seconds squared. Sorry about that. All right, if we work out the problem, all right, we're going to find that the maximum height is 31.25 meters. Okay? All right, now for our last free fall type problem. It's called the ball toss problem. And really a ball toss problem, also known as an up and down problem, is the two types of problem we just looked at split in half. All right, we have the portion where the ball goes up and the portion where the ball goes down. All right, you really need to work these problems thinking about it in these two halves. All right, as the ball goes up, this is like a tossed problem. All right, so there's going to be some initial velocity. All right, but when we reach maximum height, that final velocity is zero. All right, as the velocity values are positive and we know the acceleration is negative, the signs tell us we're working against each other. We should see the object slow down as it goes up. All right, once it reaches maximum height, it changes direction and starts to fall back down to the earth. So on that half, the initial velocity is zero and the final velocity is some value. All right, on this side, our velocity values are negative because the object's moving down, and the acceleration value is also negative because gravity is always negative. So in this case, they work together and the object should speed up. All right, now one thing to keep in mind about these initial velocities and final velocities here, all right, they should be numerically the same number, but they should have opposing signs. All right, and that change in sign is because in one direction they go up, so positive velocity. On the other side, they're coming down, so negative velocity. All right, for our graphs, we're just going to take our two graphs from before and put them together. All right, so the object starts close and slows down as it reaches maximum height and then speeds back up as it comes back down towards us. All right, so you can see we can split this in half and we have our two parts, our up portion and our down portion. Maximum height occurs when that velocity value is zero. Now this total time means that each piece is that half of that time, right? And the two times, the time it takes to go up needs to equal the time it takes to go down, all right? If we look at our velocity graph versus time, all right, it's the same general idea. We start away, or on the positive side, sorry, and we go towards zero because we're decreasing in velocity, and then we change direction to the negative side and go away from zero because we are speeding up. All right, so we're going up and then down. All right, maximum height occurs at that directional change where we go across the zero line. All right, again, this is the total time it takes for the action, and each portion, the up and the down, should be equal to each other and half of the total time. All right, so our ball will have maximum velocity in two spots this time. At the bottom, well, I guess I shouldn't say bottom because they're both the bottom. Let me change that. Let me change that wording. Let's say the beginning and at the end of the motion. All right, and as we saw before, the velocity of the ball equals zero at the maximum height, and the time it takes to reach the maximum height equals the time it takes for the ball to fall back down. All right, so let's look at one last problem. All right, this one's got a couple different parts. I've split my data table up into two pieces this time, up and down, but we've got our same variables, v initial, v final, acceleration, distance, and time. All right, so here we have Sam tossing a lacrosse ball up into the air and then catching it 3.4 seconds later. All right, so the first question is, how many seconds does it take the ball to reach maximum height? So the total time is equal to 3.4 seconds. So the time up is equal to half of that total time. So we divide it by 2, and we find that the time it takes it to go up is 1.7 seconds. So the time up is 1.7 seconds. Now, we said before the time down has to equal that, so we put a 1.7 seconds here as well. All right, let's see what else do we know. All right, we know that the acceleration is negative 10 meters per second squared, whether it's going up or down. All right, I know that if it's going up, that v final is 0, and if it's coming down, v initial is 0. All right, So now I move on to the second part. What was the initial velocity of the ball? So we're looking for V initial. All right, I look at the information I've been given, all right, and I can solve my acceleration formula for V initial here. All right, so I've got negative 10 meters per second squared equal to 0 minus V initial times 1.7 seconds. All right, so we rearrange and solve for V initial, and we find the initial velocity was 17 meters per second. All right, so that is the time it took that's the velocity we gave the ball as it left our hand, or I guess in this case, Sam's lacrosse stick. All right, then we look at what is the maximum height. All right, so again, sticking with the upside, all right, we know that distance equals V initial times time plus 1/2 AT squared. All right, and we have all this information, so we plug everything in. 17 meters per second times 1.7 seconds plus 1/2 negative 10 meters per second squared times 1.7 seconds squared. All right, a couple things. When you're working these problems, we're always going to be dealing with the half time in these problems. Don't ever go back and pull that full time in. That is a big mistake. All right. Second, don't forget to square the time before you multiply it by gravity. That's another place where we tend to see some math errors. All right, so once we calculate everything, you should find that that distance the lacrosse ball travels is 14.45 meters. All right, and that will be equal to the distance it will cover as it comes down. We just put a negative sign because it's coming down. All right, how many seconds did it take the ball to fall from its maximum height? Well, we already said that the time it takes it to go up has to be equal to the time it takes it to come down. So in this case, the time it takes it to come down must also be 1.7 seconds. All right, and then what was the velocity of the ball just before Sam caught it? So this time we're looking for V final as the ball comes back down. All right, well, I know that the initial velocity has to equal that final velocity just with that negative sign. So in this case, my final velocity should be negative 17 meters per second. And again, the negative sign is there because the object is falling down. All right, and then finally, what would your position versus time graph and your velocity versus time graph look like for this motion? All right, so if we have our axes for distance and time, all right, the object starts close to us, slows down as it reaches maximum height, then speeds up as it comes back down to Earth. So that's what our position versus time graph should look like. And then for velocity versus time, all right, we start on the positive side but slowing down, so it goes to 0. We change direction and then continue to speed up but in the opposite direction. So these are what our two graphs should look like. All right, so that should just give you a good idea about the 3 different types of motion we come into contact with. We're talking about free fall, the graphs that go along with them, and where things should be negative in terms of velocity and what our acceleration value should be. If you have any questions, let me know.